Friends, this is Shomi Bishas, and today we'll be discussing our network theorem application and analysis with that DC and AC circuit. Our today's objective is Norton's theorem. So it is a Norton's theorem is today's objective, and how to use this Norton theorem. Here in the Norton theorem, as you have understood the Thevenin's, so in the Norton theorem the RTH is same, the evaluation process and the calculation RTH is same, but instead of getting VTH, here we will find out ISC, the short circuit current first. The short circuit current with that RTH, if I am multiplying, we will be getting that VTH, right? So if that ISC will be finding out, the RTH is known to you and RL is there where you have to find out the current. So the equivalent circuit look like this. Here it is the ISC, here it is the RTH, here it is the RL. The circuit is look like this, okay? And finally you will be able to apply that Norton's theorem on that basis concept. So initially I have collected few mathematical problem and its solving process, and also application of different other circuital approaches, the circuital analysis on that same problem, to show you that whatever the approaches may be, it may be KVL, maybe KCL, maybe any other thing, Norton, Thevenin's, whatever, but if your approach is right, the answer is always same to same, okay? So let me having that class of that Norton's theorem. So as you can see here, one problem is given that in a particular circuit, as you can see in that particular circuit, so here it is 50 volt, it is 100 volt, both are DC. This is 5, 15 and 10. Three resistors are joined like a T formation. So it is a live question of the two-port network also. If you have that knowledge of Z and Y parameters, you can easily use it and find out the short circuit parameters or the Z parameters or the open circuit parameters or anything else, so depending upon how you write that equation. So basically this type of circuit is called the T circuit. It is a T-like combination. It can be easily converted to the pi circuit also. If you are converting this pi circuit, these values will be changing. How? That is a star combination. So you know that how to convert star to delta. So this particular circuit will be converted to the delta, and the same thing can be applied on this, and finally you will be able to get the requisite, okay? So fine, here if you are having the current, what is the current through that 10 ohm resistance? That is a question being asked. So how to get that? You can using that KCL first of all. That is my oldest way. So if you are using KCL, so you have to find out nodes. So here A is my node, so it is 50 minus V by 5. It is the node voltage is V, suppose, and V is the VOC, is the Thevenin's voltage. Here is the Norton's theorem, still the Thevenin's voltage is mentioned anyway. So it is 50 minus V by 5, that is V by 10, V minus 100 by 15. So it is the equation. You can easily solve what is V and what is I, because I is what? That is V by 10, so it is 4.54 ampere. Easily solve it out. You should not take Norton's, you should not take Thevenin's and other. Now using mesh, if you are taking mesh, so obviously here is I1, it is I2, two branch current is there, so 50 minus 5 I1 minus 10 I1 minus I2, one I1, another is I2, is 0, one equation. Solving the second, you will be having the second short of equation. Solving this, finally you will be getting I is what? I1 minus I2, here I1 is I2, so net I is I1 minus I2, so it is again 4.54 ampere. You can work it out by your own selves also, okay? Now come to the my point where you are using Thevenin's theorem right here. So in the Thevenin's theorem, if you are applying this thing, so you know that step 1, you have to remove this, you have to make it open, okay? No resistance is there, and you have to find out VOC. So how to get this? After removing this, the entire circuit is like a single loop, so you can easily use that KVL, and finally you'll be getting that VOC equals to this. How to get that? Here the drop across this 5 ohm resistance is, here I is 2.5, so cross 5 it is into 5, so 12.5, adding this we are getting 62.5 volt. Okay, now RTH equals to the parallel combination of 5 and 15, this is 3.75. so finally I is what? RTH plus RL. So finally the answer is this, same, this one and this one. 3 answer is same. We are using Thevenin's theorem, we are using mesh analysis, we are using KCL. Okay, fine. Now our today's objective is using Norton's theorem on that. So if you are using Norton's theorem on the same one, so how to get that? So here it is a basic circuit what I have already shown to you. This is ISC. Okay, this is ISC, short circuit current. So you have to find out the short circuit current. First of all, if you are making it short, so the current is coming from this region to this region and from this region to this region, so just like a ocean flow. So if it is shorted, so it is 0. So what is the total current? 50 by 5, this is I1 coming to this node, and another is 100 by 50 coming to this node. So this is 50 by 3 ampere ISC. Okay, and the RTH is already known to you by the previous example. So what is the Norton's equivalent circuit? This is 3.75 and 10, they are parallel to each other. As I have shown to you, these things are obviously parallel to each other, RTH and R. So in the same way, here I have just put it 3.75 and 10, the current source is given. So finally I will be getting that current divider rule here, and finally the current is flowing to this and to this also. So what is the current through this 10 ohm resistance? That is 50 by 3, that is the current, and using this current divider bias, so the final current is again 4.54 ampere. So that is a final answer using that Norton's theorem. So using Norton's theorem the answer is 4.54, using the Thevenin's theorem the answer is 4.54, using the KVL and KCL the answer is same. You can see this one and this one and this one. So finally whatever your approach may be, it may be Thevenin's, it may be Norton's, it may be superposition, anything else, but whenever you are applying these things, so obviously the final current will be same, it cannot be different. If you are having the different result, application of the different thing, different approaches to a particular circuital analysis, DC or AC, whatever it may be, you are getting different answers. So obviously your approaches are wrong, or 1 or 2 approaches may be wrong, maybe 1 approach is right. So you have to find it by yourself. So here we will be discussing another problem where you can see that 2 ampere current source, this is R2 parallel to this, it is a dependent current source 2I is given on this. This is R1, this is X, this is Y. So it is given that R1 and R2, these two, if equals to 4 ohm, find out the ISC, Norton short circuit current. Find out I short circuit for R1 equals to 2R2. So 2 conditions is given in this particular problem. So how to solve this one? First of all, I should make it in this way. Say it is 2 ampere, this is RL. So here what I have said, that is 2 ampere and that is R2, this is R1, this is a dependent current source, that is 2I. So we have to find out first of all that ISC, I short circuit current. So how you have to do this? First of all, if this is taken as node number 1 or node A, whatever, so you have to use KCL at 1. So how to find out what is the value of KCL? That is, here it is 2I, this is ISC, this is 2A. So using this, here that R1 and R2 is giving as 4 ohms. So finally it is 2 2 ampere, this is 2I, that is I, it means the short circuit current here, and this is ISC. So 2 plus 2I minus I minus ISC equals to 0. So from this you will be getting that here I plus 2 equals to ISC, and that is for the ABCD loop. Now again, if you are taking the ABCD loop again, so that is R1 into ISC of that R2 and I. So this particular current is I, what I have mentioned right here. So this is a short circuit current, so obviously here that I is flowing. So finally R1 ISC, this is R2 into I equals to 0. So solving this, you will be getting that ISC is infinite. Why? Because I equals to ISC. So you know that I equals to ISC, if we are writing this, so it should be ISC is infinite. So again, you can put R1 equals to 2R2 in this particular equation. So you will be getting that ISC equals to I by 2. So if ISC equals to I by 2, so obviously ISC equals to 2 ampere by this particular equation. So we can easily find out ISC, and if you have to find out that Norton's equivalent voltage, so that current source here, it should be converted to voltage source, that 2I, that is a current source, it may left open, or you can easily make it left open. So here this 2 point R1 and R2, they are the making that Norton's equivalent voltage, which is a Thevenin voltage, and finally that can be easily applicable by ISC with that current source, with that RL and the RTH as a parallel combination to this, and you'll be able to find out the final answer of this. So finally for this problem, the Norton circuit cannot be made. Okay, the Norton circuit cannot be made. It means if R1 and R2 is equal, so the current flow is infinite, so it will be shorted, so the circuit will not last forever. So to make it lasting, we have to make this particular combination. It means R1 should not be equals to R2. So it is my last combination I have given, that Norton's theorem only applicable if this is not equal only, otherwise Norton's theorem is not applicable for R1 equals to R2. Okay, so this is all about the DC analysis, what I have studied, what you all have seen, that is a DC analysis of that Norton's theorem, of the Norton theorem application of the DC circuit. In the next class we'll find out some other mathematical problems of that same Norton application on that AC circuit. So the rules of the AC circuit will be same as I have discussed in the Thevenin's one. So here in the Norton's, we have to see how to use the Norton theorem in different type of AC circuit in my next class. So thank you very much of all of you for pleasant listening, and see you all next. Have a nice day. Bye bye.